grounding to metallic water pipes is not universally permitted. In areas where it is disallowed, alternative grounding methods must be employed. Two common and effective alternatives are the Ufer ground system and the ground ring. The Ufer ground system, also known as a concrete encased electrode, utilizes the reinforcing steel within a building's foundation. This system creates a low-resistance pathway to the earth, often proving more effective than traditional driven ground rods. The concrete encasing the rebar helps protect it from corrosion and provides a large surface area for contact with the earth, further reducing resistance. The components of a Ufer ground system include the concrete encased electrode itself, which is typically at least 20 feet of bare zinc galvanized or other electrically conductive coated steel reinforcing bar or rod, not less than 0.5 inch in diameter, encased by at least 2 inches of concrete and located within and near the bottom of a concrete foundation or footing that is in direct contact with the earth. The reinforcing steel must be electrically connected using methods such as welding, exothermic welding, pressure connectors listed for the purpose, or other approved means. A ground ring involves burying a number 2 American wire gauge copper wire in a trench around the building's perimeter. This trench should be at least 2 feet deep. The copper wire is then connected to grounding rods and the main grounding electrode, establishing a low resistance path to the earth from multiple locations. This distributed grounding system enhances safety and reduces the risk of electrical faults. The components of a ground ring include the number 2 American wire gauge bare copper wire, grounding rods, which are typically 8 feet in length and made of copper or copper-clad steel, and listed connectors suitable for direct burial. The copper wire must be buried in direct contact with the earth and form a continuous loop around the building. Spacing of the grounding rod should be determined by local codes in soil conditions, but a minimum spacing of 6 feet is generally recommended. An alternative method, using a number 2 ground wire connected to number 4 rebar in the footing, can also be acceptable, provided certain requirements are met. Firstly, the number 4 rebar must be installed in accordance with local building codes. Secondly, the number 2 ground wire must be connected to the rebar at a depth of at least 4 feet below the surface. Thirdly, the connection must be made using a listed grounding clamp. Finally, the number 2 ground wire must be run to the grounding rods and the meter base. When selecting a grounding system, the Ufer ground system presents several advantages. 1. Lower resistance than driven rods can be expected. 2. It provides multiple paths to earth. 3. It is less susceptible to corrosion or damage. 4. It meets the requirements of many local building codes. These advantages make the Ufer ground system a reliable and effective grounding solution. Resistance is a critical factor in grounding system performance. Lower resistance ensures a more effective path for fault currents to flow back to the source, tripping circuit breakers and minimizing the risk of electrical shock. Driven ground rods can be affected by soil conditions such as dryness or high resistivity, leading to higher resistance. The Ufer ground system, with its large surface area in contact with the earth, typically exhibits lower and more stable resistance. Multiple paths to earth provide redundancy and improve the overall reliability of the grounding system. If one path becomes compromised, others remain available to carry fault currents. The Ufer ground system, with its connection to the building's foundation, offers multiple paths through the concrete and reinforcing steel. Ground rings, with their perimeter loop of copper wire and multiple grounding rods, also provide multiple paths to earth. Corrosion and physical damage can degrade the performance of grounding systems over time. Driven ground rods are exposed to the elements and can corrode, particularly in acidic soils. The Ufer ground system, encased in concrete, is better protected from corrosion and physical damage. Ground rings buried underground are also less susceptible to damage than exposed grounding components. Compliance with local building codes is essential for any grounding system. Codes vary depending on the jurisdiction and may specify requirements for grounding electrode type, size, installation methods, and testing. The Ufer ground system is recognized by many building codes and is often preferred due to its superior performance. However, it is always necessary to verify specific code requirements with the local building department. In addition to these alternative grounding methods, several other considerations are important for ensuring effective electrical grounding. These include the size and type of grounding conductors, the quality of connections, and the proper bonding of metallic components. Grounding conductors must be sized according to the National Electrical Code (NEC) or applicable local codes. The size of the grounding conductor is determined by the size of the service entrance conductors. Larger service entrance conductors require larger grounding conductors. Grounding conductors must be made of copper or other approved materials and must be protected from physical damage. Connections in the grounding system must be made using listed connectors and must be properly tightened to ensure a low resistance connection. Loose or corroded connections can increase resistance and compromise the effectiveness of the grounding system. Bonding is the process of connecting all metallic components of the electrical system to the grounding system. This includes metal conduits, metal enclosures, and metal water pipes. Bonding ensures that all metallic components are at the same potential, reducing the risk of electrical shock. The NEC provides detailed requirements for bonding. Regular inspection and testing of the grounding system are essential for ensuring its continued effectiveness. Ground resistance testing can be performed using a ground resistance meter to verify that the grounding system is providing a low resistance path to earth. Visual inspections can identify any signs of corrosion, damage, or loose connections. Any deficiencies identified during inspection or testing should be promptly corrected. When installing a Ufer ground, ensure the following steps are taken. Firstly, the reinforcing steel must be clean and free of rust or coatings that could impede electrical conductivity. Secondly, the concrete must be in direct contact with the earth. Thirdly, the connection between the reinforcing steel and the grounding conductor must be made using a listed connector. When installing a ground ring, ensure the following steps are taken. Firstly, the trench must be deep enough to provide adequate protection for the copper wire. Secondly, the copper wire must be buried in direct contact with the earth. Thirdly, the connections to the grounding rods must be made using listed connectors. Several factors can affect the performance of a grounding system. These include soil conditions, moisture content, temperature, and the presence of corrosive substances. Soil resistivity is a measure of how well the soil conducts electricity. Low soil resistivity is desirable for effective grounding. Soil resistivity varies depending on the type of soil, its moisture content, and its temperature. Sandy soils typically have higher resistivity than clay soils. Moist soils have lower resistivity than dry soils. Warm soils have lower resistivity than cold soils. The presence of corrosive substances in the soil can accelerate the corrosion of grounding electrodes and conductors. This can increase resistance and compromise the effectiveness of the grounding system. In areas with corrosive soils, it may be necessary to use corrosion-resistant grounding electrodes and conductors. Grounding systems play a critical role in electrical safety. A properly designed and installed grounding system can protect people and equipment from electrical shock and damage. It is essential to understand the principles of grounding and to follow all applicable codes and standards when designing and installing a grounding system. The National Electrical Code (NEC) provides comprehensive requirements for electrical grounding. The NEC is updated every 3 years and is adopted by most jurisdictions in the United States. The NEC covers all aspects of electrical grounding, including grounding electrode systems, grounding conductors, bonding, and equipment grounding. In addition to the NEC, many local jurisdictions have their own electrical codes and regulations. It is important to check with the local building department to determine the specific requirements for grounding systems in your area. Grounding is not the same as bonding, though they are related. Grounding connects the electrical system to the earth, while bonding connects metallic parts of the electrical system together. Both grounding and bonding are necessary for electrical safety. Grounding provides a path for fault currents to flow back to the source, tripping circuit breakers and minimizing the risk of electrical shock. Bonding ensures that all metallic parts of the electrical system are at the same potential, preventing voltage differences that could cause electrical shock. A ground fault circuit interrupter GFCI is a device that protects people from electrical shock by detecting ground faults. A GFCI works by monitoring the current flowing in the hot and neutral conductors. If there is a difference in current between the two conductors, it indicates that current is leaking to ground. The GFCI will trip and interrupt the circuit, preventing electrical shock. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas. Surge protection devices, SPDs, protect electrical equipment from voltage surges. Voltage surges can be caused by lightning, power outages, or other electrical disturbances. SPD work by diverting the surge current to ground, protecting the equipment from damage. SPD are typically installed at the service entrance and at individual pieces of equipment. Electrical safety is a shared responsibility. Everyone should be aware of the hazards of electricity and take steps to protect themselves and others from electrical shock and fire. When working with electricity, always follow safe work practices and use appropriate personal protective equipment. If you are not qualified to work with electricity, hire a qualified electrician. Electricity is a powerful force that can be dangerous if not handled properly. By following safe work practices and using appropriate safety equipment, you can protect yourself and others from electrical hazards. Remember to always de-energize circuits before working on them. Use insulated tools and equipment. Wear appropriate personal protective equipment, such as rubber gloves and safety glasses. Never work in wet or damp conditions. Be aware of the location of overhead power lines. Maintain a safe distance from electrical equipment. If you are not qualified to work with electricity, hire a qualified electrician. Regular maintenance of electrical systems is essential for safety. Inspect electrical equipment regularly for signs of damage or wear. Replace damaged or worn parts promptly. Test ground fault circuit interrupters, GFCIs, regularly to ensure they are working properly. Keep electrical panels and equipment clean and free of obstructions. Have electrical systems inspected by a qualified electrician periodically. Electrical fires can be caused by a variety of factors, including faulty wiring, overloaded circuits, and misused electrical equipment. If you discover an electrical fire, do not use water to extinguish it. Water can conduct electricity and increase the risk of electrical shock. Use a fire extinguisher that is rated for electrical fires. Call the fire department immediately. Prevention is the best way to avoid electrical fires. Have electrical systems inspected regularly by a qualified electrician. Do not overload circuits. Use electrical equipment properly. Replace damaged or worn electrical cords and plugs. Keep flammable materials away from electrical equipment. Install smoke detectors and carbon monoxide detectors. Test smoke detectors and carbon monoxide detectors regularly. Develop and practice a fire escape plan. In conclusion, electrical grounding is a critical aspect of electrical safety. By understanding the principles of grounding and following all applicable codes and standards, you can protect yourself and others from electrical shock and fire. Remember to always check with your local building department to determine the specific requirements for grounding systems in your area.